Thank you. Okay. Okay, so, but I think it's working, so let's start. So I want to discuss what I call the p-adic method. Maybe it's better to call it a p-adic method. Yeah. And it's a method to study groups of birational transformations and problems coming from dynamical systems involving algebraic transformations. So I want to start with, as an introduction, with two examples, or maybe three. And then I mean, these are two examples to motivate the method, and at the end of the series, of course, I will prove how to deduce two examples from the p-adic method. Okay, so the theorem I will state do not involve p-adic numbers, but to prove them, we shall use p-adic numbers. So here is the first theorem. So this is due to Jason Bell. And in fact, Jason Bell, and then a paper by Bell, Gioca, and Tucker. So this is Dragos, Gioca, and Tom Tucker. And in fact, this theorem, I will state it for algebraic transformations, but initially it was proven for linear transformations by Skolem, and then Mahler, and then Lech. And I will explain maybe tomorrow or the day after why Skolem, Mahler, and Lech. Okay, here is the statement. You start with X, which is an algebraic variety. Over C or over a field of characteristic 0. And then you give yourself f from x to x, an automorphism. So it is important that f is invertible, or at least that f is étal. Okay, so the Jacobian determinant does not vanish. And then you start with a point x in X, and with a variety Z in X, a subvariety. Okay, so these are your initial data, and you look at the orbit of the point X under the dynamics of F. Okay, so you get a sequence of points, X, F of X, etc., Fn of X, and you list the times n such that Fn of X is contained in Z. So this I call the visiting times. So I will denote it by like this. It's the visiting time of the point X in the subvariety Z under the dynamics of F. So this is just a set of number of integers, let's say n in Z, such that Fn of X is contained in Z. Okay. So this is just because it's an automorphism. It's an automorphism, so I can reverse it. If F is just an étal endomorphism, I just iterate positively. Okay. Okay. And the conclusion is that this set is a finite union of arithmetic sequences okay. So it's a union that So it's a subset of the integers, but it's a finite union of sets of the following type: R I k plus Si, where k is in Z. Okay, the sum is finite, 1 to L. Okay, and you see, this is what I call an arithmetic sequence. Of step Ri starting at Si. I'm not assuming that Ri is non-zero. So when Ri is 0, this set is just one point, one integer. Okay. So the important corollary or the consequence is that if this set of visiting times is infinite, then it contains an infinite arithmetic sequence R k plus S k in Z, which means that the event that the orbit visits Z is a periodic event. It occurs periodically, okay? At least along this subsequence. Is it clear? Is the statement clear? Okay. Okay, so here is an example. You look at a sequence like that, un plus, let's say, okay, so that's a linear sequence which is given by some linear recursion. Okay, pi is just 3.4. Okay, square root of 2 is square root of 2. Okay, and you start with the point so an initial data, so you need to specify U0, U1, U2. Okay, that's the initial data. So it plays the role of X. And consider a hyperplane Z, which is given by some linear form in 3 coordinates. Okay. And then you look at the set of times such that the point un plus 2, let's say un plus 1, un plus 2 is contained in Z. So this is just the same type of problem as the last one, but everything here is linear. Okay, so this set of time, or this. So this is a subset of the set of integers. Here I put in n. And it's a finite union of arithmetic sequences. This finite union of arithmetic sequences depends on the linear form that you chose. Okay. So that's an example, and this example is the one I mean, this type of examples is the one that was studied by Skolem-Mahler-Lech. Okay. And more precisely, Skolem at the beginning, I mean, the first paper he wrote concerned such linear recursive sequences, and he was interested in the indices n such that un is 0. This corresponds to take a z to be the hyperplane defined by the first coordinate to be 0, which corresponds to taking the equation psi of z1, z2, z3 to be just z1. Okay, so if you have, so the upshot is, if you have a linear sequence, by this I mean a sequence defined by such a linear recursive relation, then the set of indices such that un vanish is a finite union of arithmetic sequences. And so we will prove this theorem by proving the more general result, which I stated here. Is it good? What? Finite is not one. You will see that in the proof. It's not constructive at all. So it's an open problem to, I mean, to write an algorithm to decide whether such an arithmetic sequence vanishes or not. Okay, so this is an open problem. Okay, so that's the first thing I want to discuss. Yes, that's it. The second thing is a consequence, in fact, of. So here is the theorem. So okay, let me write it like that. Let F, so I consider the affine M space, so dimension M, that's the affine space. And I take a polynomial automorphism. Okay. And I will put an index Z here for the ring of integers. Okay. By this, I mean that F is defined by polynomial formulas with integer coefficients, as well as the inverse of F. Okay, so that's my data. The first statement is if F acts transitively on the set of integer points, so this is just z to the m, then in fact m is 1, and f of x is x plus 1 or x minus 1. Okay, if you take the translation by 1 on the line, of course it acts transitively on the integers. Okay, if you start with any integer, you can move to the left or to the right to any other integer. So this is an example. In fact, it's the only example. Second statement is if every orbit of F in AM of Z, so you just look at integral orbits, is periodic, then in fact the period is uniformly bounded, and this says that F has finite order. So these type of statements are not so easy to prove, and in fact are easy corollaries of the theorem I stated on the left. So if you know what are p-adic numbers and so on, you can try in the remaining part of this hour to prove the second statement using the first one. Okay, here is the second theorem. So the theorem I want to state is the following. I mean, is in the following type of questions. Okay, so what we have done so far, we looked at the Cremona group or groups like that, and we wanted to understand this group from at least two perspectives. An external point of view, what are the possible quotients? What are the homomorphisms for the Cremona group to another group? Okay. Does there exist non-trivial quotients, or what is the same, that there exist interesting non-trivial normal subgroups? Okay. So this is what Stefan will discuss, and we also discussed that last week with the mini courses by Evgeny Schindler. Okay. There is also an intrinsic point of view, which is what is the structure of this group? Is it a billion, not a billion? Can I generate this group by elements I know well? Things like that. And there is also another point of view. You give yourself another group that you like. And you want to know whether this group that you like can be embedded into the Cremona group. If yes, in which dimension? What is the smallest dimension such that your group can be embedded in the Cremona group? Okay? Here is a statement which I obtained with Junichier. Okay. Suppose that X is an irreducible projective variety over C, and assume that the group SL n of Z, so the group of n by n matrices with coefficients in Z and determinant 1. So take this group and suppose that this group embeds into the group of birational transformations of X over C. Okay, by this I mean that there is a homomorphism from this countable group to this group of birational transformation, which is injective. That's what I mean by embeds into. Then the dimension of X is at least n minus 1. And in case of equality, you can find a birational map from X to Pn minus 1. And a homomorphism from your group to PGLN of C such that I mean the action of SLNZ on X is conjugate by phi to the action of the image of this homomorphism rho in Pn1 minus 1. Okay, so this is for every gamma in SLNZ. Phi composed with gamma is the image of gamma by this homomorphism composed with phi. Okay. In other words, if you start with an action of SLNZ on X, if the dimension of X is n minus 1, you can conjugate this action to a projective linear action on Pn minus 1. Okay. So to this, I need to add a few comments. In fact, you can replace SLNZ by So you can replace SLNZ by any finite index subgroup in SLNZ. Okay, so instead of starting with an action of SLNZ, you take a finite index subgroup in SLNZ and you assume that gamma embeds into the group of birational transformations, and then you get the same conclusion, but you have to replace SLN by gamma here. So this is the first remark. It's stable. This statement is stable when taking a finite index subgroups. The second thing I want to say is that if n is larger than 2, strictly, so n is 3 or 4 or more, in fact, you know all possible injective homomorphism from SL and Z into PGL and C. The first one is just the standard embedding. You know, SLN is contained in GLN and you project in PGLN. Or you can compose by the automorphism of PGLN, which takes a matrix and maps it to the inverse transpose. Okay. So in fact, you have only two choices here. And the same is true for finite index subgroups. Okay. Okay, so it's a very rigid situation in case of equality. That's the statement. So you completely understand what happens regarding the problem of embedding SL and Z or finite index subgroups in birational transformation groups. Last remark is that, in fact, this statement works if you replace X, let's say, by a quasi-projective variety and the action of gamma by an action by automorphisms. Okay. Then the conclusion is the same. The dimension must be at least n minus 1. And in case of equality, then the action is conjugate to an action of PGLN. I mean, if I start with as an assumption that the action is by automorphism, then at the end, the conjugacy is not birational, but it's just an isomorphism. Okay? And I don't need to assume X projective. A quasi-projective is okay. This type of statement, you see, maybe you say, why should I care about this statement because I don't like SL and Z? Okay. But let's say you like projective varieties or quasi-projective varieties defined over a field K of characteristic 0, and you want to understand the group of birational transformation and how it depends on X. This statement says that if I increase the dimension, I will increase, I mean, let's say I'm talking about the Cremona group. If I increase the dimension, then I will increase the group of birational transformations, because for a given dimension, I can find SL and Z in my group, but not for a smallest one. Okay. And in fact, this statement works over any field of characteristic 0, and this was the first proof of that. Okay. Okay. Or it works also for automorphisms of the affine space. For instance, the group of automorphisms of AN contains SL and Z. The group of automorphisms of AN minus 1 does not contain SL and Z. Okay. So it's useful to describe automorphism groups or to understand better automorphism groups and groups of birational transformations. No. No. Okay, so what I want to do now is describe the proof of this statement, or at least sketch it, And for that, I need this so-called p-adic method. Okay. I started at 5 or 10? 5. Okay. So I need to follow my notes because otherwise I will forget to say. Okay, so I know that some of you don't know much about p-adic numbers, so I want to to introduce you to them. So define p-adic numbers. Then I will explain that, we will do some analysis with p-adic numbers, like writing power series, taking derivatives, try to understand when a power series is converging and what is the radius of convergence, this type of questions. But in fact, don't be afraid. P-adic numbers, it works much better with them than with complex numbers. At least for the question I will look at. Okay, so first, the p-adic absolute value. Okay, so if you have a field K, an absolute value for me is a map from K to the positive, non-negative real numbers. Okay, so this is I will denote it like that, such that, okay, first, the absolute value of an element x, x in K is 0, if and only if x is 0. Okay. Second thing, you have your triangular inequality, absolute value of x plus y is bounded from above by the sum of the absolute values. And the third property I want is multiplicativity. So x times y has absolute values of x times absolute value of y. Okay? Now if 2 is replaced by, let's say, 2 prime, which is x plus y is bounded from above by the maximum of the absolute values. Then we say that the absolute value is non-Archimedean or ultrametric. Yeah. Okay, so you already know examples. You know the absolute value on R. You know the absolute value on, the modulus on the complex numbers. And here I want to introduce the p-adic absolute values over the field Q. Okay, so I pick P a prime number. Okay, and I fix it. Okay. And now, if I take an integer, a, I can write a is plus or minus 1 times p to something, to some power, times b, where, so I will make the power precise, where p does not divide b. If you prefer, p and b are coprime. And so the power here, I will denote it by Vp of A. So it's a p-adic valuation of A. So it's just a positive or non-negative integer. Okay. And then I define, for an integer, I define absolute value of A with respect to P. So I will write P as an index at the beginning, but then I will forget about it. It's just P to minus VP of A. Okay. And now if I have a point X in Q, I write X as A divided by D, the numerator and the denominator, and I define the p-adic absolute value to be the ratio of the p-adic absolute values of these numbers. Okay? Okay, so this is the definition of my absolute value. Okay. Okay, so what is important is the fact that this is an ultrametric absolute value. There is something I didn't say. It's you know, if A is non-zero, I can write this like that. If A is equal to 0, then A is divisible by P to the n for every n. So I define the p-adic valuation of A to be plus infinity and the absolute value to be 0. Okay. So let me add it here. Absolute value of 0 is 0 by definition. Okay. Okay, so let me explain why it's an absolute value. I will do it by looking at integers instead of rational numbers. So the absolute value is 0 if and only if x is 0. Yes, this is clear, it's by definition. The product, so third property. So if I multiply two numbers, okay, like x is p to something times something which is coprime to p, and y is p to something else times something which is coprime to p, then the product is p to the sum of the exponent times something which is coprime to p. Okay, so the exponents, you add them, and the absolute value, you multiply them. So this is also clear. Okay. So what is the second property? The second property is that if, let's say, if p to the n divides x, and p to the m divides y. You take the minimum between n and m, and then p to this minimum divides x and y, so it divides the sum. And that's it. Okay, you get less than max of the absolute values. Okay, so this is an ultrametric absolute value. Moreover, something you should keep in mind is that the product over p prime, so you take all possible primes, and you compute the absolute value of x with respect to this choice of p. So this gives you a contribution given by all possible primes, and then you multiply by the usual absolute value. Okay, I will put infinity, so it's just the usual one. Then this is 1. For all x in Q except 0. Okay. And why is it so? It's because x, I mean, if x is an integer, x is plus or minus 1 times the product over p prime p to the vp of x. Okay. So just the decomposition of x into prime factors. Okay, and from this you get this product formula. Okay, so in average, the p-adic absolute values, they compensate the usual absolute value. Also, what you should know, but I will not use it, is the fact that every absolute value on Q is equivalent to one of the p-adic absolute values or the usual one. And by equivalent, I mean that one is the power of another. Okay. Or if you prefer, two absolute values are equivalent if they define the same topology. So what is the topology associated to the absolute value? It's given by the distance. It's just distance between 2 points x and y is the absolute value of the difference. Okay. And by definition, if you have an absolute value on a field, then you have a distance on this field, then you have a topology using balls. Okay. So 2 points are close if the distance between them is small. So this gives you a topology. This also gives you a notion of Cauchy sequence. And so this gives you a notion of completion. Okay, you can ask, is my field complete with respect to this distance? And if it is not, you can complete by using Cauchy sequences. And this is what you do to construct QP. Okay, so let's say B, look at okay, so I consider the disk of radius 1, I mean the closed disk of radius 1 in QP. Okay. Centered at the origin. Okay, so let me denote it like that. Okay, so it's a set of points now in QP at distance less than 1 from the origin. Okay. I should write the closed unit disk. So this disk it contains Z, okay, the set of integers. So it contains its closure, which I denote by ZP. So again, I started with Q with a p-adic absolute value, which gives me a distance I complete by using Cauchy sequences. And then, of course, the absolute value extends, or the distance extends by definition to QP. And it defines an absolute value on QP. And now I define these two notions, so the unit disk, the closed unit disk, and the closure of the set of integers. Okay, so I want to show that, in fact, ZP is the same as a disk of radius 1, a closed unit disk. So what is the point in there? So you first, Z is contained in the unit disk. By definition, the p-adic absolute value of an integer is p to the minus the valuation. So it's at most 1, and it is equal to 1 if and only if the integer is not divisible by p. Okay, so Z is contained in this disk. So the closure of ZP is contained in this disk. So what I need to show is the opposite inclusion, that this closed unit disk is contained in ZP. Okay, so how do you do that? So you start with a point in this set, and by construction, it's a limit of elements xn in Q, limit in the sense of p-adic distance. Okay, so the absolute value of x is at most 1. And here, the limit of the absolute value will be the absolute value of x. And the absolute value of a rational number is p to some integer. So the possible values for this sequence, they live in p to the z, okay, all possible powers of p. But at the limit, it must be at most 1. So for n large enough, it is less than 1, because this set is discrete. Okay. So this means that I can write xn as a quotient, like that, where maybe an is divisible by p, but bn is not. Okay, this is the meaning of this inequality for n large enough. Okay. So if I prove that 1 over bn itself is a limit of integers, then xn will be a limit of integers, and so x will also be a limit of integers. Okay, so I only need to show that if b is not divisible by p, then 1 over b is contained in the closure of Z. Okay, that's what I need to show. Is it clear? I mean, I want to be basic at the beginning so that you manipulate a little bit p-adic numbers. But if you do not understand this beginning, you will be lost tomorrow. So okay, so it's not hard, but when you see it for the first time, maybe it goes too quick. No? Okay, so I say it again. X, you can approximate it by xn. Xn is an times 1 over bn. So if 1 over bn can be approximated by an integer, xn will be approximated by a product of integers, an times the integers, and so x will be also approximated by an integer, and so I will be done. Okay, so I just need to show that 1 over b is a limit of integers. Okay, and this, if I remember well, is Bezout's theorem, but not the one we used last week. Okay. You see, you start with Q with the p-adic absolute value, and you take the completion QP, okay? So I didn't write it, but I said it. The p-adic absolute value was a map from Q to R plus. But when you complete, it extends to a map which I denote by the same notation from QP to R plus, which is an absolute value on QP. I mean, QP is a field. It is an absolute value on QP with image, let's say, when you look at, I mean, image is 0 union p to the z, all possible powers of p. Okay? Does this answer your question? Okay. Okay, so now I want to show that 1 over b is a limit of integers. And I say, so I fix k, on 1. Then b and p to the k are coprime. So there exists ck and dk in Z such that ck times b minus dk times p to the k is 1. So this is Bezout's theorem, you know, but the one from arithmetic. Okay. So this means that ck times b minus 1 is dk times p to the k. And when I take absolute values, I can put the absolute value here. dk, its absolute value is at most 1 because it's an integer. And the absolute value of p to the k is p to the minus k. Okay, so this difference is very small. And now you just invert b. And this is less than 1 over absolute value of b. You see? So now the sequence of integers ck that I constructed converges towards 1 over b as k goes to infinity. So this concludes the proof that 1 over b is the limit of the sequence ck. Okay, right? Okay. Okay, so doing this, I have proven that ZP is a closed unit disk. Now I can use power series. Okay, let me write it like that. Suppose that xk is a sequence of elements in QP. Such that xk in p-adic absolute value goes to 0 as k goes to infinity. then the sequence, the series sum of the xk for k larger than 1 converges in QP. And this is obvious, okay? Because you see, for every positive epsilon, there exists a k, k0. For every k larger than k0, by definition, the absolute value of xk is less than epsilon. Okay, so if I write this series, after some index, all the terms are less than epsilon. So you write the series, it's x1 plus x2 plus blah, blah, blah. Plus at some point you have xk0, and then you continue. And all these terms are less than epsilon in absolute value. Okay. But then by the ultrametric property, when you sum terms which are less than something, the sum is less than the maximum. So this the contribution of the sum in absolute value is less than epsilon. Okay, by the ultrametric property. If you keep adding things which are small, the sum is small with the same upper bound. Okay, so the series converges. Okay, so that's a very useful fact in p-adic analysis, and how I can use it is as follows. It's a way to write p-adic numbers let me give an example. How does it work? It's let me compute 1 over 1 minus p. Okay. You see, p as an element of QP is small. Its absolute value is 1 over p. So if you use the usual series expansion of 1 over 1 minus x, you get sum for k larger than 0 of p to the k. And this goes to 0 when k goes to infinity. So minus 1 is equal to p minus 1 sum k larger than 0 of p to the k. So minus 1 is also in the closure of the set of positive integers. Okay, this series is made of positive terms, and it converges toward minus 1. So the closure of n is the set of non-negative integers. Minus 1 is also in the closure of this. So the disk of Fourier-1, when I take the closure, it's like Zp, that is the closure of Z, and this is also the closure of N. Okay, and now I can write an expansion for every number in this disk. So maybe I should say that Zp, so it's a closed unit disk. This is what I proved, and it is also called the ring of p-adic integers, right? That just by definition. So I want to write an expression in terms of series for every element in this ring. So what I say is pick x in Zp, write x as a limit of element xk, where is xk in n. Okay, and then you can write xk like that. You can look at the p-adic expansion of xk. So every integer, you can write it a0 plus a1 to the p times p plus a2 times p squared plus blah 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 plus a k to the times p to the k for some k. And for some ai, which are taken between 0 and p minus 1. Okay? Every integer, you can write it like that. Is it clear for you? Or? Yeah. Oh, yes, you're right. Let's say my sequence is xn, and here it's k. Okay? There is still a mistake? Is it good? Okay. Now, the fact that this sequence converges towards x means that, in particular, that the absolute value of the difference xn minus xm goes to 0. Okay? But what is the distance between 2 points? So you write like that. Okay. You see, if the difference a0 minus b0 is not 0, then xn minus xm is not divisible by p, and then the distance between xn and xm is 1. So to read the distance between the two, I look at the coefficients in the formula which are equal, and then when I see two coefficients which are not the same the first time, I read the index, and the distance is p to the minus of this index. Okay, so if xn goes to x, this implies that this sequence of numbers a0 converges at each places. It stabilizes. Okay, and then I declare that x is given by the corresponding series. And this gives me a way to write every p-adic integer as such a series. So I will write this, and I think I will stop. Yeah. Let me write it as a theorem. So every element x in ZP can be written in a unique way as x is a sum for k larger than or equal to 0, ak p to the k, with the ak between 0 and p minus 1. Okay. So you see I did it for minus 1 above instead of x. So that's what I wanted to say. So this gives homeomorphism. So this I let you prove as an exercise. From what? From 0 p minus 1 power n. So sequences like that to ZP. So to a sequence of such integers, I associate the series and its value in QP, which in fact is in ZP. Okay, so you see this set, here I say it's a homeomorphism, so I put the product topology on the left. This set is a Cantor set. Yeah. So that's part of the exercise. So on the left, you have a Cantor set. On the right, you have ZP. And ZP is homeomorphic to a Cantor set. Okay. Okay, so that's it for today. I think it's time now. And what I will do tomorrow is do analysis with p-adic numbers. Okay. What I did today is, if you compare to real numbers, I defined real numbers, and I said that every real number can be given by a decimal expansion. Okay. This is what I did today, but in the QP setting. So I define the absolute value, the completion, and I'm saying that every p-adic integer can be defined by such a p-adic expansion. That's it. Yes. The uniqueness of the representation of what? Of SLNZ, you mean? Of representation of SLN into B Pn minus 1 if n is at least 3. Because, you know, if you take SL to Z, SL to Z is contained in PGL to C and acts on P1. But SL to Z, I mean, what is interesting is PSL to Z, which is Z mod 2 star Z mod 3 of free product with no amalgamation. And there are many ways to put an involution and an element of order 3 in PGL2. So this is not rigid when n is equal to 2, but starting with 3, it's very rigid. There are just two possible injective homomorphisms. Yes. Okay. Into Pn, I think I can do that. If you go to Pn plus 5, you cannot do it because you can always do this trick that you take the standard action of SLNZ on Pn, then you multiply by so how does it work? Okay, how does it work? The trick is to use varieties which are stably rational but not rational. Okay, you know the trick. Okay. So using this trick, you see that if you try to find a classification of all possible actions of SLNZ on pk, where k is large with respect to n, and large is like n plus 3 is sufficient, okay, then the number of possibilities is at least as large as the number of stably rational varieties in dimension k minus n. And we have no ID for that. Okay. Yeah? No, no, you're right. When at the very beginning, when I described some consequences, I said something wrong, and then I said, suppose we are in the Cremona group. Okay, so a consequence of what we proved with Juni, I mean this third theorem, is that the Cremona group, let's say, over the field of rational numbers, when you increase the dimension, then the Cremona group, okay, so let me write it. The Cremona group, let's say, over the field of rational numbers, in n variable, this one contains SL n plus 1 of Z. Okay? If you look at this one, where M is less than N, it does not contain SLN plus 1 of Z. Okay? By the theorem. I mean, this is not possible by the theorem we proved. So this one is strictly larger than that one in this sense, that it contains this group, but this one does not. Okay? If you want to prove the same statement over the field of complex numbers, there are other techniques using the fact that the field of complex number is not countable. But if you want to prove this over Q, I think, I'm not sure, but at that time this was the first proof. And I think now it's also the only proof we have, but I'm not completely sure. Okay. So this is what I meant. If you replace Cremona group over Q in dimension n by bir x, where let's say x is a n-dimensional variety defined over Q, then of course it depends a lot on the geometry of x. Okay, so what I wanted to say is just for the Cremona group. Does it answer your question? I guess so, yes.